All right, so we're continuing on. The next topic I'll be reviewing is simple harmonic motion. So here we go. Normally denoted SHM for simple harmonic motion. The first example that's common in AP physics problems is the pendulum. That, of course, will swing back and forth after released. The angle is often used to measure the angular position of the pendulum. It's typically released from rest and will, rotate or swing back and forth. Some of the main concepts that are important in this picture are energy concepts. The initial kinetic energy would be 0 because it's not moving. And if it's going to swing down to, let's say here, the lowest position, all of its initial energy is potential energy. Whatever H initial is, multiply that by its weight, mg. And so the point is the mechanical energy at the top, E, is really just potential energy. There's no kinetic energy. And then all of that kinetic energy gets converted into, all of that potential energy gets converted into kinetic energy as it swings downwards. And so when it gets toward the bottom, the total energy will be just kinetic energy at this final point here. There'll be no kinetic energy at the top and no potential energy at the bottom because it's at its lowest point, and it's a nice conversion from potential to kinetic energy. Again, if that meant there was 100 joules of kinetic energy, if there was 100 joules of potential energy up at this highest point, then there would be 100 joules of kinetic energy at the lowest point, meaning those things are equal, and it means the total energy must be equal. That's based upon the conservation of energy idea. Of course, after it passes through the center point and starts going upwards, up to here, the reverse cycle is what happens, and it starts slowing as it goes up this to a higher point, and therefore the kinetic energy drops, the potential energy goes up, and if there was no friction or air resistance, then this would be a perpetual motion machine, and it would just continue going back and forth forever, always returning to the exact same height on the other side. It would come right over to here, be at the exact same height, and it would have 100 joules of potential energy. And again, no kinetic energy at this point. It would stop. And then it would swing back down, and this would just go back and forth, back and forth. At the halfway point right here, which looks like it's about the halfway point, it would be a 50-50 split of energy. It would be 50 joules of kinetic energy and 50 joules of potential energy. If it were right here, only 25% of the way down, then it would have 25 joules of kinetic energy and 75 joules of potential energy. And the opposite, if it was 75% of the way down, then most of the energy has been dissipated as kinetic energy, and it would have 75 joules of kinetic energy and only 25 joules of potential energy. Always adding up to 100, though. That's the important point, is that if the initial potential energy is 100 and there were truly no air resistance forces or frictional forces, nothing to remove energy from the system, then at any point along that path, that object's total energy would always be 100 joules if it started at the top of the 100 joules. So if it started up here with 100 joules of total energy, when it's here, E is still 100 joules. When it's down toward the bottom, E is still 100 joules. The total energy would always be 100 joules because there's nothing to remove energy from it. And so there would be a continual transfer from kinetic to potential, and then from potential back to kinetic, and so forth as it went back and forth, and it would do that forever. which would be called perpetual motion. And from what we know of, that's not allowed in any earthly examples. There's no way of removing all air resistance and friction forces. You can minimize them, but you can't actually get rid of them. And so the motion would continue for a while, as a typical pendulum would, but certainly a few minutes later it would eventually stop. The other comment about a pendulum is the period of a pendulum is 2 pi times the square root of L over G. So the length of a pendulum is just considered L. And note that the period does not depend on that original amplitude angle. This theta here would be considered amplitude. And the period is independent of how far back you bring it before you release it. You can bring it back just a few inches and have a very small theta and release it. It might take 5 seconds to go all the way there and all the way back. That's called 1 cycle, and that amount of time is called the period. All the way there and all the way back is the period of a pendulum. Or you could have drawn it back much further and had a much larger amplitude and released it, and shockingly it takes the exact same amount of time to go all the way there and all the way back, which is why there's no amplitude in this formula. It's dependent only on the length of the pendulum, and it's only dependent on how much gravity there is, because gravity is actually what provides the torque that causes rotation. So when you have a pendulum like this, gravity is pulling straight down with its object's weight, and there's 2 components to that. This bit right here is perpendicular to R, if this is the ceiling here. So this would be considered R, and this perpendicular component produces a torque, because any force that's perpendicular to the line that connects that object and the pivot point, R, produces torque, and torque produces rotation, and that's why pendulums rotate in a gravity environment. But if you did this in the space station where there's effectively no gravity, G would be 0, and you could release it and it wouldn't move at all. If you went to Jupiter, where gravity is very strong, the torque would be much stronger. G would therefore be increasing, and the period would decrease. So it means it would go back and forth very, very rapidly on a strong gravity environment. If you went to Pluto, where G is really tiny, there's much less gravity, and therefore things weigh less on Pluto, then G will be a very small number, and T will be alternatively a very large number, meaning it will take a long time. On Pluto, it would go there, very slow, and very, very slow to go back, and very slowly go there again, very slowly go back. It'll be a very long period on Pluto. G is very tiny. There's very little torque placed upon any object at the end of a pendulum, and therefore it would take a long time to go through 1 cycle. Again, on Jupiter, back and forth, back and forth, back and forth very rapidly, period would be tiny. Notice again, the mass of the object does not ultimately affect the period, nor does the amplitude, nor does air resistance. The period of a pendulum, it shows in the equation, depends only on the length of the pendulum and gravity. Okay, the other kind of common simple harmonic motion that you're expected to know about in the AP exam is the mass spring system. Most of the time, I'd say over 90% of the time, they show it as a spring that is on a flat table, and then there's a mass sitting on the end of it, and then you would pull it to stretch out the spring all the way to here, where the initial velocity would be 0, and then you would release it, and it would go flying backwards past the equilibrium position. This would be the equilibrium position, and it would continue in the leftward direction until it compressed the spring like this, and this would also be a 0 velocity because it stops at this position, and it would just go back and forth. So this would be like, I did a little out of order, but this would be like A, B, and C in terms of a series of events. The important part here is to note that when the velocity is 0, the kinetic energy would be 0. So you have no kinetic energy on the endpoints. Here and here, there's no kinetic energy. However, all of the energy is stored energy, so it's all spring energy, elastic potential energy. Typically, we would write this, that the potential energy is 1/2 k delta x squared. However, since this is simple harmonic motion, the full displacement is called the amplitude. That would be the distance from wherever it originally started all the way to here. That's called A, the amplitude. And so you can substitute in for delta x, just the symbol A for amplitude, recognizing that if this was a 5 centimeter displacement from equilibrium all the way over to the right side, then when it goes all the way to the left side, that would also be 5 centimeters. Amplitude is always symmetrical on both sides of displacement. And so in terms of energy, all of the energy is potential energy over here on the right side. All of the energy on the left side is also potential energy, because when you compress a spring or stretch a spring, you store energy because it takes work to do either stretching of a spring or a compressing of a string. It takes, I keep saying string, a spring. It takes an applied force and a displacement in both cases, stretching or compressing. And so you do work in both cases, and therefore energy will be stored in the spring based on the conservation of energy, regardless of whether you stretch it or compress it. And you reference that potential energy in an equation here. And recognizing on the endpoints, there's no kinetic energy because the object's motionless and stopped. All the energy is stored as potential energy on the endpoints. But then as it returns, remember, after you release it, it accelerates faster and faster towards equilibrium. So when it passes through this equilibrium position right here in the middle, this is where the velocity is a maximum. And that means all of your energy is kinetic energy. All kinetic energy at that point, and no potential energy at that midpoint, because at the midpoint, the spring here is not stretched or compressed. It's at its nice, normal, relaxed length, and therefore you can't have any stored energy in a spring that's not stretched or compressed. And that's the reason there's no potential energy stored in the spring right there in the midpoint. That means all of your energy would be kinetic energy. And so if you were looking at values for that, just means as you stretch it all the way out to here and you released it, if there was 50 joules of spring potential energy, that means right when it passes through the center point, it'll be 50 joules of kinetic energy. And then when it's fully compressed, all the way over here, it would still be 50 joules of potential energy. Yet again, just like the pendulum, it was no different than the pendulum. The pendulum has potential energy on the endpoints, no kinetic energy on the endpoints, and all kinetic energy in the center when a pendulum is going back and forth. It's the same thing here. All of the energy is potential energy on both endpoints when it's fully stretched or fully compressed. No kinetic energy on the endpoints, just like the pendulum, because it stops. And all of the energy is converted into motion energy or kinetic energy right at the center. And therefore, at the center, there's no potential energy, all kinetic. Okay, maybe a couple equations that would be potentially useful. Not going to derive them by any means right now. But for this case that we're talking about, when the mass is all the way at the end versus all the way at the center versus fully compressed, the maximum velocity is always equal to the amplitude times the angular frequency. So this here represents angular frequency. Of the mass spring system. And so omega is always a square root of k over m. And so if you were trying to develop that equation a bit further, because they're never going to give you what omega is. All they ever provide is the spring constant, k. They provide that, and they would tell you what the mass of whatever the mass is for the block. They'll give you that. And note that those two given things can always be used to calculate what omega is. And that would get inserted right here. And so the maximum velocity right at the center is a times the square root of k over m. And then if you were asked what the kinetic central point, well, really all you'd have to do is reference whatever the potential energy is all the way at the end point. If you could calculate whatever this is, and it came out as 50 joules, then the kinetic energy at the center must be 50 joules. Don't bother going through 1/2 times m times v squared and then having to reference this for v. It's a waste of time. Just use the concepts to save yourself that headache and recognize that all potential energy is turning into kinetic energy at the center. Last little bit will be on graphs. If you saw yourself a position versus time graph, because remember this block goes back and forth between 3 positions, right? Goes all the way there and then comes all the way back and so forth, keeps repeating this. Well, if you call this the x-axis and you call this x equals 0, this might be x equals 5. That means this over here would be x equals -5. Who knows, maybe centimeters. I don't know what the unit would be for distance. But the point is that if you were to graph that thing's position versus time, you'd have a positive part of the axis you'd want to use and a negative part of the axis that you'd want to use to reflect the idea that this thing at sometimes has a positive position over here, and at sometimes it has a negative position over on this side. And so this thing this graph would look like this. This is called sinusoidal motion. It's a sinusoidal graph. And since you typically are stretching this spring all the way out and releasing it, that normally means that at t equals 0 seconds, it has some position. Here it would be 5 centimeters. And therefore, when it reaches the midpoint right here, x equals 0, that would correspond to this point right here. When it reaches the -5 position, that would correspond to right here. This is -5 now, centimeters. And then, of course, as it starts returning, it would start getting closer and closer to the 0 again, and you'd be riding up the curve right here. It would eventually again pass through the center again, and yet you'd be again here, and you get the point. It would go back and forth, back and forth. The period goes from here to here. This is the period of this oscillation. Again, the period of a spring, I don't know if I showed it before, but this is 2 pi times the square root of m over k. And so when they give you, if they wanted you to make a calculation, you'd have to know what the physical mass of the block is. You would need to know what the physical spring constant k is, and you could plug those values in, and you could get a numerical value for the period. It's how long it takes to go through one cycle, which would be all the way from where you release it, all the way back to the full compression, and then all the way back to here yet again. That's one period. And on a graph, that period is reflected as the distance from crest to crest. An equation that models this, x as a function of time, would be a cosine omega t. A is your amplitude. Again, it depends upon how far you've drawn it back before releasing it from the midline. So amplitude would go from here to here. And that number for amplitude goes here. And just remembering also that omega is always the square root of k over m times t. This would be considered a model for this motion. Whether you would actually have to calculate something with it, I really don't think so. Whether you'd have to actually derive some sort of model for it, I really don't think so. But knowing that it is there as a model to model the motion, just be aware of it. Also recall that the slope of a position versus time graph is velocity, right? So the slope of this graph gets sharper and sharper as you get towards the central point. And so velocity is maximum at that point because the slope is greatest at that point. That's right when it's at the center. That's when it's moving at a really fast speed. And that very fast speed is related to the slope right there. Because after it passes through that point, you see that the slope of the tangent line starts decreasing and decreasing. And then the slope of the tangent line right here slope equals 0 right at this point, because that corresponds to when it's turning around. The spot right here is right here, and it stops. And so since the slope is 0, that means the velocity is 0 there. All right, maybe like 1 more minute, 2 more minutes. I think that's pretty much it. Just pointing out that the maximum position is always the amplitude for this mass spring system. The maximum velocity is always the amplitude times omega, which is a times k over square root of k over m. And it turns out that the maximum acceleration, I don't know that you'll have to reference that in your exam, but it might turn up, is a omega squared, which is really just a k over m, because this bit right here is omega. And so if you square it, it just undoes the square root and provides a k over m. And that maximum acceleration actually occurs at the endpoints. Occurs at the endpoints when the force is greatest. Because remember, acceleration is proportional to force. So as the spring goes from a fully compressed state all the way through the midpoint, and then all the way over here to where the spring is all the way stretched out, this is where the maximum force occurs. Maximum force occurs at the end when it's not moving. When the object is actually stopped, the spring is exerting the greatest force at that moment, because the spring is either fully stretched out, and according to Hooke's law, a fully stretched out spring will exert a lot of force on you, or the spring is fully compressed, and according to Hooke's law, a spring will exert a large force on you when you fully compress it. Noticing that in the middle, when you pass through equilibrium, the spring is not compressed or stretched. So that's a relaxed spring there, and therefore the spring force is 0 in the center. All right, I believe that concludes what I wanted to talk about for simple harmonic motion in a nutshell. Hope you found that helpful.